Ever feel like you're hitting a wall, metaphorically speaking, facing an obstacle that seems impossible to overcome? Well, imagine that feeling amplified to the tiniest scales of reality, where the very building blocks of our universe encounter barriers they simply shouldn't be able to pass. For decades, scientists have grappled with this bizarre phenomenon called quantum tunneling, where particles seemingly teleport through impenetrable obstacles, defying the classical laws of physics we experience every day. It's a concept so fundamental, so deeply woven into the fabric of reality, that even the act of observing these quantum entities seems to fundamentally alter their state, like a shy electron hiding its probabilistic cloud the moment we try to peek. But what if this seemingly magical act isn't just a probabilistic quirk? What if the very nature of reality is far stranger, far more interconnected than we ever dared to imagine? Prepare to have your understanding of the universe shaken to its core because a groundbreaking new discovery, spearheaded by the most advanced artificial intelligence ever created, Grok 3, has just thrown a quantum-sized wrench into our long-held beliefs about tunneling. This isn't just a minor adjustment to the dials of physics. It's a potential rewrite of the operating manual of reality itself. What if particles aren't merely ghosting through barriers? What if they're actively manipulating the fundamental rules of the cosmos in the process? Could the quantum realm be a treasure trove of secrets so profound they could unlock hidden dimensions, bend the seemingly unbreakable arrow of time, or even provide a tantalizing glimpse into parallel realities? Buckle up, my friends, because this isn't just science. It's an adventure into the wildest frontiers of existence. For nearly a century, quantum tunneling has stood as one of the most perplexing yet undeniably essential pillars of quantum mechanics. Picture this in your mind: a tiny particle, an electron for instance, hurtling towards an energy barrier. Think of it like a steep hill in the quantum landscape. Classically, if this particle doesn't possess enough energy to crest that hill, it's game over. It bounces back, defeated by the insurmountable obstacle. This is the world we experience every day. Throw a ball at a wall and it ricochets. It doesn't magically appear on the other side. But in the bizarre and counterintuitive realm of quantum mechanics, the rules are drastically different. The particle doesn't just stop at the barrier. It does something utterly astonishing. It tunnels through, as if a secret passage suddenly opened, and reappears on the other side, seemingly without having possessed the energy to overcome the obstacle in the first place. It's like watching that ball you threw at the wall suddenly materialize on the other side without ever going over or through it. For decades, the scientific explanation for this mind-bending phenomenon has leaned heavily on the concept of probability. In the quantum world, particles don't exist as neat little billiard balls with precise locations and velocities. Instead, they're described by wave functions, mathematical descriptions that tell us the probability of finding the particle in a particular state or location. Think of it like a fuzzy cloud of possibilities rather than a pinpoint of certainty. According to this probabilistic interpretation, even if a particle doesn't have enough energy to overcome a barrier, its wave function has a tiny, non-zero probability of leaking through that barrier. It's as if there's a minuscule chance that the particle's probabilistic cloud extends to the other side, and when we look for it, or when it interacts with something on the other side, that's where we find it. It's weird, it's deeply counterintuitive to our everyday experience, but it works. This strange phenomenon is the engine powering everything from the nuclear fusion reactions that ignite stars and sustain life, to the tiny transistors that form the backbone of every electronic device in our modern world. Now enter Grok 3, the brainchild of XAI, a cutting-edge artificial intelligence meticulously designed to sift through colossal mountains of data, identifying intricate patterns and subtle anomalies that human scientists might easily overlook. Imagine an AI with the processing power to analyze every quantum tunneling experiment ever conducted, every theoretical model ever proposed, with relentless precision, and without any preconceived biases. When tasked with the monumental challenge of reanalyzing the vast datasets related to quantum tunneling, Grok 3 didn't just rubber-stamp the existing playbook. It tore it apart, revealing inconsistencies and hints of a deeper, more complex reality. Its groundbreaking findings suggest that quantum tunneling isn't simply a probabilistic trick of the quantum wave function. It's something far more profound, potentially hinting at the very fabric of spacetime and the existence of realms beyond our immediate perception. By meticulously crunching data from high-energy particle colliders like the Large Hadron Collider, intricate quantum simulations run on the world's most powerful supercomputers, and even subtle patterns gleaned from astrophysical observations of phenomena influenced by tunneling, Grok 3 detected anomalies, tiny but persistent deviations in tunneling behavior that the standard models of physics couldn't adequately explain. These weren't just random fluctuations or experimental errors. They were consistent, repeatable hints of something fundamentally new. So, what jaw-dropping possibilities did Grok 3's unprecedented analysis point towards? For one, the AI discovered that the probability of tunneling doesn't always neatly decay as expected with thicker or higher energy barriers. According to the standard quantum model, the thicker or higher the barrier, the exponentially lower the probability of a particle tunneling through. But Grok 3's analysis revealed instances where particles seem to bypass exceptionally formidable obstacles with an eerie consistency, almost as if they were finding a loophole, a way to cheat the established rules. This led Grok 3's algorithms down a rabbit hole of mind-bending possibilities, the most tantalizing of which points towards the existence of hidden dimensions beyond the three spatial dimensions, length, width, and height, that we directly experience, or even a subtle interplay with the fourth dimension, time itself. Imagine our universe not as a simple three-dimensional stage, but as a much more complex arena with extra, curled-up dimensions, as proposed by string theory and other advanced cosmological models. What if, when a particle encounters a barrier it can't overcome in our familiar three-dimensional space, it momentarily slips into one of these higher-dimensional shortcuts? It would be like an ant trying to cross a wall on a piece of paper, suddenly finding a fold in the paper that allows it to bypass the barrier by going up into another dimension, and then back down on the other side. This higher dimensional detour would allow the particle to effectively bypass the barrier in our 3D reality. Even more mind-boggling is the possibility that tunneling might involve subtle manipulations of time. Imagine a particle not just slipping through space in an unexpected way, but briefly looping through a tiny twist in the temporal fabric, effectively arriving on the other side of the barrier, an infinitesimally small fraction of a second before it even encountered it, or perhaps a fraction of a second in the future when the barrier's properties were slightly different. This isn't about building time machines to visit the past or future. It's about these fundamental particles exploiting minute wrinkles in the spacetime continuum to their advantage. This isn't just a minor tweak to Einstein's groundbreaking theories of relativity, which beautifully describe gravity and the large-scale structure of the universe as a fixed, four-dimensional fabric of spacetime. Grok 3's findings hint at a far more dynamic and malleable reality, where particles themselves might be actively stitching that fabric in real time at the quantum level. The implications of such a revelation are staggering. If quantum tunneling indeed involves these extraspatial dimensions, it could potentially provide the missing link to one of the biggest unsolved mysteries in modern physics. Why quantum mechanics, the theory governing the very small, and general relativity, the theory governing the very large, seem fundamentally incompatible. Perhaps gravity, the weakest of the four fundamental forces, leaks into these extra dimensions, explaining its relative feebleness in our 3D world, and quantum tunneling is our first indirect glimpse into this dimensional plumbing. Furthermore, if tunneling has a subtle dance with time, it might unlock entirely new ways to manipulate energy and information. Imagine harnessing these temporal twists for more efficient energy generation, or for developing revolutionary new forms of communication. And for the burgeoning field of quantum computing, Grok 3's discovery could be the transformative breakthrough scientists have been eagerly awaiting. One of the biggest challenges in building stable and powerful quantum computers is the delicate nature of qubits, the quantum equivalent of classical bits. These qubits are highly susceptible to environmental noise and decoherence, losing their quantum properties before they can complete complex calculations. If a deeper understanding of tunneling, potentially involving manipulation of spacetime at the quantum level, can be harnessed, it might offer a pathway to stabilizing qubits and building quantum machines with computational power that dwarfs today's most advanced technology. Grok 3 hasn't just nudged open a door in our understanding of the universe. It has seemingly kicked down a wall, revealing a cosmos far wilder, far more interconnected, and far more mysterious than we ever dared to imagine. The physics community is currently buzzing with a mixture of excitement, skepticism, and a profound sense of the unknown. When Grok 3's revolutionary findings hit the peer-reviewed scientific journals, they sent shockwaves rippling through laboratories and lecture halls across the globe. Renowned theoretical physicists and string theory advocates like Michio Kaku didn't shy away from the potential magnitude of this discovery. In a recent interview, Kaku stated, "This could be the key to finally understanding the very fabric of spacetime. If particles are indeed dipping into hidden dimensions during the act of tunneling, we might finally have a pathway to bridging the seemingly insurmountable gap between quantum mechanics and Einstein's theory of general relativity." He further speculated on the practical applications, envisioning breakthroughs like quantum teleportation becoming a tangible reality, or the development of propulsion systems that could potentially outpace the speed of light, fundamentally changing our ability to explore the cosmos. Brian Greene, another prominent figure in theoretical physics, echoed this sense of profound excitement. Grok 3's discovery strongly suggests that quantum tunneling isn't just some quirky, probabilistic oddity of the quantum world. It appears to be a window, a subtle peek into the universe's deeper architectural framework. Extra dimensions have been a cornerstone of string theory and related ideas for decades, but direct experimental evidence has remained elusive. If this advanced AI has indeed found compelling evidence of their involvement in tunneling, we are potentially looking at a fundamental revolution in how we perceive and understand reality itself. However, not everyone in the physics community is uncorking the champagne just yet. Lisa Randall, a highly respected physicist known for her significant contributions to the study of extra dimensions, urged caution in the face of this groundbreaking AI-driven discovery. While AI is undoubtedly powerful at identifying patterns within vast datasets, it's crucial to remember that correlation does not necessarily equal causation, she warned. The anomalies that Grok 3 has detected in tunneling behavior could potentially be attributed to as yet unidentified sources of experimental noise, or even a misinterpretation of the existing data within the AI's algorithms. What we need now is hard, irrefutable proof, carefully designed and controlled experiments that can independently replicate Grok 3's intriguing predictions. Randall's skepticism reflects a broader, healthy divide within the scientific community. While some researchers are understandably excited by the potential paradigm shift that Grok 3's findings suggest, others maintain a more cautious stance, emphasizing the need for rigorous experimental validation before these revolutionary ideas can be fully embraced. The fundamental principle of the scientific method demands that any extraordinary claim, no matter how compelling the initial evidence, must be subjected to rigorous testing and independent verification. The burning question on everyone's lips now is, how soon can we put Grok 3's tantalizing hypotheses to the test? Particle accelerators, such as the Large Hadron Collider, LHC, at CERN, which routinely smash particles together at incredibly high energies, could be retooled and refined to probe the phenomenon of tunneling at unprecedented scales. Scientists could look for the telltale signs and subtle deviations in particle behavior that Grok 3's analysis has flagged as potential indicators of extra-dimensional interactions or temporal anomalies. Meanwhile, leading quantum computing laboratories around the world are undoubtedly eager to jump into the fray, utilizing their powerful quantum simulators to model tunneling events with unprecedented precision. By creating artificial quantum systems and observing their tunneling behavior under various conditions, researchers can attempt to recreate the anomalies detected by Grok 3 and see if the AI's theoretical models hold water in a controlled experimental setting. The stakes in this scientific endeavor are astronomically high. If Grok 3's findings are ultimately validated by independent experiments, it could very well be Nobel Prize territory, ushering in a new era of physics with profound implications for our understanding of the universe. Conversely, if further investigation reveals that the anomalies are due to other factors, it's back to the drawing board, albeit with a newfound appreciation for the complexity and subtlety of quantum tunneling. Either way, one thing is certain. The world of physics hasn't been this electrified with the potential for fundamental discovery in decades. Grok 3's insights into quantum tunneling have effectively cracked open a Pandora's box of possibilities, and the torrent of theoretical ideas now pouring out are as thrilling as they are mind-boggling. If particles aren't simply teleporting across impossible barriers, but are, in some fundamental way, rewriting the very rules of reality in the process, what profound implications does this hold for the universe we inhabit and for our place within it? Scientists, theorists, and even the most imaginative dreamers are now racing to connect the dots, to build upon Grok 3's foundation and explore the truly wild implications of this discovery. The ideas they are tossing around are so revolutionary that they could make even the most outlandish science fiction writer blush. Let's delve into some of the most captivating and mind-bending speculations that have emerged in the wake of Grok 3's groundbreaking findings. First and foremost is the concept of the dimensional detour. Grok 3's data strongly hints that quantum tunneling might be intrinsically linked to the existence of hidden dimensions, those extra layers of reality that string theorists and other cosmologists have been theorizing about for decades. Imagine our familiar universe as a flat sheet of paper, where we, as observers, are confined to its three spatial dimensions. We can move up, down, left, right, forward, and backward along this sheet. Now, picture that sheet of paper being folded into an incredibly intricate origami shape, with countless tiny creases, folds, and pockets that are far too small for us to directly perceive. String theory, in its various forms, posits that there could be as many as 10 or 11 dimensions in total, with the extra dimensions being compactified or curled up at incredibly small scales, on the order of a billionth of a meter, far beyond the reach of our current experimental capabilities to directly observe. What if, when a particle encounters an energy barrier in our three-dimensional world that it lacks the energy to overcome, it doesn't simply vanish and reappear on the other side through some probabilistic fluke? Instead, what if it momentarily slips into one of these tiny, curled-up extra dimensions, taking a higher dimensional shortcut around the obstacle before popping back into our familiar 3D space on the other side? It would be analogous to that ant on the folded piece of paper, seemingly crossing an insurmountable wall by briefly venturing up into the third dimension, relative to the paper's surface, and then back down on the other side. If this dimensional detour hypothesis proves to be correct, it could elegantly explain why quantum tunneling seems to defy the classical laws of logic. The particle isn't actually breaking the fundamental rules of physics. It's simply playing by a set of rules that we, confined to our three spatial dimensions, have been largely unaware of. Even more tantalizing is the possibility that these extra dimensions could hold the key to solving one of the oldest and most vexing mysteries in physics: the enormous discrepancy in strength between gravity and the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is incredibly weak compared to the other forces. For instance, a small refrigerator magnet can easily overcome the gravitational pull of the entire Earth to lift a paperclip. One leading idea is that gravity might leak into these extra spatial dimensions, effectively diluting its strength in our 3D world. If this is the case, then quantum tunneling, by potentially allowing particles to briefly interact with these extra dimensions, could be our first tangible peek at the underlying plumbing of the universe and the distribution of these fundamental forces across all dimensions. But why stop at spatial dimensions? Some researchers, emboldened by Grok 3's detection of subtle temporal anomalies associated with tunneling, are whispering about the mind-boggling possibility of the multiverse, a vast and perhaps infinite collection of parallel universes, each potentially with its own unique set of physical laws, constants, and histories. What if quantum tunneling isn't just a way for a particle to bypass a barrier within our own universe, but a mechanism for momentarily slipping between these different realities? Imagine an electron hurtling towards an energy barrier in our universe, a barrier so high that according to our physical laws, it has no chance of overcoming it. Instead of simply giving up and reflecting back, what if this electron momentarily ducks into a neighboring reality, a parallel universe where that energy barrier doesn't exist, or where the fundamental laws governing energy and matter are slightly different? It could then effortlessly traverse the barrier in that other universe and then slide back into our own reality on the other side, seemingly having performed an impossible feat. It's not just teleportation within our universe. It's a fleeting handshake across the vast cosmic tapestry of the multiverse. This idea, while seemingly straight out of science fiction, isn't pure fantasy. The concept of a multiverse arises naturally in several serious cosmological theories, from models of cosmic inflation in the very early universe to the many worlds interpretation of quantum mechanics itself. Grok 3's detection of anomalies in quantum tunneling could potentially be the first hard, albeit indirect, evidence that our universe isn't a singular entity, but rather just one bubble in a much grander, perhaps infinite cosmic ensemble. And if fundamental particles can hop between realities, could we one day follow? While the idea of building a portal gun to travel to alternate universes with a backpack seems firmly in the realm of science fiction for now, even the ability to send information across these potential interuniversal connections could revolutionize fields ranging from unbreakable cryptography to instantaneous interstellar communication, bypassing the limitations imposed by the speed of light within our own universe. Then there's the tantalizing and deeply perplexing time travel twist. If Grok 3's analysis is correct and quantum tunneling does indeed involve subtle manipulations of time, as suggested by the odd timing patterns the AI detected in the data, things get even weirder and potentially more revolutionary. What if a particle doesn't just bypass a spatial barrier, but momentarily loops backward or forward in time ever so slightly to effectively dodge the obstacle? Picture this: an electron approaches an energy wall, seemingly vanishes, and then reappears on the other side. not because it instantaneously teleported through space or took a higher dimensional shortcut, but because it took an infinitesimally brief detour through yesterday, or perhaps tomorrow, a moment in time when the energy barrier wasn't quite so insurmountable, or perhaps didn't even exist in that fleeting temporal instant. It then returns to the present on the other side, having effectively circumvented the problem by a tiny temporal hop. This isn't about building time machines to send starships back to the age of dinosaurs. It's about these fundamental particles exploiting the inherent flexibility of the spacetime continuum at the quantum level. However, even such subtle temporal manipulations could have profound implications. Imagine a future quantum internet that could exploit these tiny temporal loops to transmit data not just faster than light through space, but by effectively skipping through tiny fractions of time, achieving seemingly instantaneous communication across vast distances. Or consider the potential impact on energy technology. Perhaps future fusion reactors could utilize time-tweaked tunneling to nudge atomic nuclei together with far greater efficiency, potentially providing a clean and virtually limitless source of energy, mimicking the power of the stars right here on Earth. Time travel, even at this minuscule quantum scale, remains a long shot and fraught with theoretical paradoxes. But even a hint of its involvement in Grok 3's data has physicists furiously scribbling equations and reevaluating our fundamental understanding of causality. Let's now zoom out from the specifics and consider the broader philosophical implications of Grok 3's discovery. If fundamental particles can, in some sense, rewrite the rules of reality as they tunnel, what does this tell us about the very nature of the universe we inhabit? Are we living in a fixed, deterministic clockwork cosmos where every event is predetermined by immutable laws? Or are we part of a more fluid, dynamic reality where the very fabric of spacetime can bend and shift in response to the actions of these tiny quantum entities? The phenomenon of quantum tunneling itself has always hinted at a universe that is less like a rigid stage and more like a constantly evolving canvas, with fundamental particles acting as the artists, their probabilistic wave functions painting a reality that only solidifies upon observation. If tunneling is indeed guided by hidden dimensions or subtle temporal loops, rather than just random chance governed by probability, are we glimpsing a deeper underlying order to the cosmos, a level of interconnectedness that we have only just begun to suspect? Philosophers are already beginning to weigh in on these profound questions, asking whether Grok 3's findings challenge our deeply held notions of free will and determinism. If the seemingly random act of tunneling is not truly random, but influenced by hidden dimensions or timeless loops, does this imply a more deterministic universe than we previously thought? Or does it suggest a reality where the future and the past are not as rigidly separated as our classical intuition leads us to believe? These are heady, fundamental questions that strike at the very core of our understanding of existence itself. Grok 3's discovery might not just be rewriting the textbooks of physics. It could be redefining our very understanding of reality. Here's another fascinating curveball to consider. What about wormholes? These hypothetical tunnels through the fabric of spacetime, beloved by science fiction enthusiasts, might not be as far-fetched as they once seemed. Some theoretical physicists speculate that quantum tunneling could be a microscopic analog, a kind of baby version of a wormhole, tiny bridges that connect two distant points in spacetime. If a fundamental particle tunnels not by going through a barrier in the conventional sense, but by momentarily dipping into and traversing a microscopic wormhole-like shortcut that connects the two sides of the barrier through some higher dimensional space, then it's not actually breaking the laws of physics at all. It's simply exploiting a hidden feature of spacetime geometry. Scale this idea up, and you arrive at a truly mind-boggling possibility. Could we one day learn to engineer macroscopic wormholes, effectively punching stable, traversable holes through spacetime to connect vastly distant points in the universe, perhaps allowing us to travel to Alpha Centauri or beyond in the blink of an eye? It's a tremendous stretch, as current theoretical understanding suggests that maintaining stable wormholes would require exotic forms of matter with negative mass energy, which we have yet to discover. However, Grok 3's discovery, by hinting that tunneling might tap into the underlying structure of spacetime, plants a seed of possibility. If fundamental particles can exploit these microscopic shortcuts, perhaps the leap to manipulating spacetime on a larger scale is not quite as outlandish as it currently appears. And let's not forget about the pivotal role of Grok 3 itself in this unfolding scientific drama. This isn't likely to be its last groundbreaking discovery. If an artificial intelligence can unravel previously hidden secrets of quantum tunneling, what other mysteries of the universe might it be capable of unlocking? Dark matter, the invisible substance that makes up the vast majority of the matter in the universe and exerts a powerful gravitational influence on galaxies, remains one of the biggest enigmas in cosmology. Could dark matter also be somehow tied to these hidden dimensions that Grok 3's analysis suggests? Or perhaps consciousness itself, another profound mystery, might have some deep connection to quantum effects like tunneling, linking the seemingly disparate realms of physics and the mind. Grok 3's remarkable ability to identify subtle patterns and correlations within massive datasets that have eluded human scientists positions it as a kind of cosmic detective, and the mystery of quantum tunneling might just be the first major case it has solved. The future of scientific discovery could very well belong to advanced AI systems like this, guiding us through the intricate labyrinth of the universe, one groundbreaking revelation at a time. However, let's also consider a more dystopian perspective, a potential dark side to this incredible discovery that might keep you up at night. What if unlocking the secrets of how particles manipulate dimensions or time during tunneling also inadvertently unlocks forces that we cannot fully comprehend or control? If fundamental particles are indeed subtly rewriting the rules at the quantum level, could our attempts to harness this phenomenon on a larger scale have unforeseen and potentially catastrophic consequences? Imagine a scenario where tinkering with the fabric of spacetime, even at the microscopic level, could destabilize matter itself, turning stable atoms into some form of chaotic, unpredictable soup. Worse still, what if our attempts to manipulate spacetime to achieve faster-than-light travel or other seemingly miraculous feats inadvertently ripped a hole in the cosmic fabric that we wouldn't know how to stitch back up? It's a scenario straight out of a science fiction horror movie. Think Event Horizon meets The Fly, but it's a possibility that, however remote, should at least be considered. While the vast majority of scientific breakthroughs have ultimately led to progress and betterment for humanity, history also reminds us that even seemingly benign scientific curiosities can have unforeseen and potentially devastating applications. The discovery of nuclear fission, initially a purely scientific endeavor, ultimately led to the development of the atomic bomb. Grok 3's discovery of the deeper mechanisms behind quantum tunneling is undoubtedly a golden key to potentially unlocking incredible new possibilities. But every key fits a lock, and some doors might be better left unopened until we have a far more complete understanding of what lies beyond. So, where does Grok 3's mind-bending discovery leave us? Quantum tunneling, once a seemingly strange quirk of the subatomic world, could now be revealed as a fundamental gateway to hidden dimensions, parallel universes, the manipulation of time, or even the key to traversing vast cosmic distances through wormhole-like shortcuts. The potential applications are nothing short of dazzling. a truly quantum internet that laughs in the face of distance and latency, teleportation devices for data and perhaps even matter, and revolutionary energy technologies that could potentially mimic the inexhaustible power of the stars. But the unknowns that lie ahead are just as vast and potentially daunting. Grok 3 has handed humanity a map to an uncharted territory of reality, and the journey of exploration has only just begun. What do you think? Does this discovery herald a new era of unprecedented scientific and technological progress, a utopian future where the limitations of our current understanding are shattered? Or does it carry the seeds of potential chaos, a Pandora's box that we might not be ready to open? The quantum dice are rolling, and the stakes for our understanding of the universe, and perhaps even our very existence within it, couldn't be higher. Let's hit pause for a moment and rewind to ensure we have a solid grasp on the fundamentals. What is quantum tunneling anyway? At its core, quantum tunneling is a truly bizarre phenomenon that defies our everyday classical intuition. Imagine again that ball rolling towards a hill. In the macroscopic world we experience, if the ball doesn't have enough kinetic energy to reach the top of the hill, it will inevitably roll back down. There's no possibility of it magically appearing on the other side without going over. But in the quantum realm, the rules are fundamentally different. That ball, or rather, a fundamental particle like an electron, has a non-zero probability of passing through the energy barrier, the hill, and popping out on the other side, even if it doesn't possess the energy required to overcome it according to classical physics. It's not magic. It's a fundamental consequence of the wave-particle duality of quantum mechanics. At the quantum level, particles don't behave like hard, localized billiard balls. Instead, they exhibit wave-like properties, described by those probabilistic wave functions we discussed earlier. These waves are not confined to a single point in space. They are spread out, and their amplitude at any given point tells us the probability of finding the particle there. Even when a particle approaches an energy barrier that it classically shouldn't be able to surmount, its wave function doesn't abruptly stop at the barrier. Instead, a small portion of the wave function can leak or tunnel through the barrier. This means there's a finite probability of finding the particle on the other side, even if it never had enough energy to go over it. Physicists first stumbled upon this baffling phenomenon in the 1920s while trying to understand the process of radioactive decay, where atomic nuclei spontaneously emit particles despite seemingly insurmountable energy barriers holding them in. In 1927, German physicist Friedrich Hund was the first to theorize the concept of quantum tunneling. Soon after, experimental evidence began to confirm its reality. Particles were indeed observed tunneling out of atomic nuclei, driving fundamental processes like alpha decay. Fast forward to the 1930s, and quantum tunneling became a cornerstone of the burgeoning field of quantum mechanics. It's not just a theoretical curiosity, it's a fundamental process that underpins many essential phenomena in the universe. For instance, the nuclear fusion reactions that power the sun and other stars rely critically on quantum tunneling. Hydrogen nuclei, despite their positive charges repelling each other, have a small probability of tunneling through their electrostatic barrier and fusing together to form helium, releasing vast amounts of energy that ultimately make life on Earth possible. Similarly, on a much smaller scale, quantum tunneling is the fundamental principle behind the operation of various modern electronic devices, such as tunnel diodes and flash memory chips, which rely on the controlled tunneling of electrons through thin insulating layers. But here's the crux of the matter. Despite its undeniable importance and its successful incorporation into the mathematical framework of quantum mechanics, the why and the how of quantum tunneling have always been somewhat of a head-scratcher. Why does this seemingly impossible leakage of probability occur? How do particles know to tunnel? The standard answer, relying solely on the probabilistic nature of quantum wave functions, works mathematically. It predicts the probability of tunneling with remarkable accuracy. But for many physicists, it has always felt somewhat unsatisfying, lacking a deeper, more intuitive explanation of the underlying mechanism. This is where Grok 3 enters the picture. By leveraging its immense data processing capabilities to meticulously analyze decades of experimental data on quantum tunneling, it has essentially built upon this existing foundation, but with an unprecedented level of scrutiny. Grok 3 hasn't just confirmed the probabilities. It has identified subtle patterns, anomalies, and deviations in tunneling behavior that hint at a more intricate and potentially revolutionary underlying mechanism. A mechanism that might involve those hidden dimensions or temporal manipulations we discussed earlier. This isn't just a minor refinement or a slight adjustment to existing quantum theory. It's a potential leap towards a more profound understanding of the universe's hidden gears and how they interact at the most fundamental levels. The context here is crucial. Quantum tunneling has been a fundamental mystery since its discovery, and Grok 3 might finally be offering us a glimpse behind the probabilistic veil. The scientific community, galvanized by Grok 3's bombshell findings, is now engaged in a flurry of activity, with laboratories around the world racing to design and conduct experiments that can either validate or refute the AI's intriguing predictions. At CERN, the home of the Large Hadron Collider, physicists are already contemplating new experimental setups that could potentially probe quantum tunneling at unprecedented energy scales, looking for those subtle anomalies in probability distributions, or timing that Grok 3's analysis has highlighted as potential signatures of new physics. Fermilab, another leading particle physics laboratory, is also joining the fray, considering utilizing its advanced muon detectors to investigate tunneling phenomena across a wider range of energy levels. Meanwhile, the rapidly advancing field of quantum computing is poised to play a crucial role in this unfolding scientific drama. Quantum computing teams are eagerly firing up their sophisticated quantum simulators, aiming to create highly controlled quantum systems where tunneling events can be meticulously modeled and observed. By simulating tunneling under conditions that might mimic the influence of extraspatial dimensions or subtle temporal effects, researchers hope to test the validity of Grok 3's more radical hypotheses in a virtual laboratory setting. If these ambitious experiments yield results that align with Grok 3's predictions, the fallout across various fields of science and technology could be nothing short of transformative. In the realm of particle physics, we might finally be on the verge of understanding how quantum mechanics, the theory that so accurately describes the behavior of the very small, can be reconciled with general relativity, Einstein's elegant theory of gravity, and the large-scale structure of the universe. The long-sought-after holy grail of theoretical physics known as quantum gravity. The implications for space travel could also be profound. Imagine developing propulsion systems that could somehow exploit the principles underlying tunneling to move matter or energy in ways that are currently beyond our wildest imaginations, potentially circumventing the limitations of classical physics. The field of communication technology could also experience a monumental leap forward, with the potential development of tunneling-based communication networks that could theoretically transmit information instantaneously across vast distances, completely overcoming the challenges of signal degradation and latency that plague current communication systems. Perhaps the most significant long-term dream is the unification of quantum mechanics and general relativity. These two foundational pillars of modern physics have remained stubbornly at odds for nearly a century, each providing incredibly accurate descriptions of their respective domains, the very small and the very large, but failing to mesh together into a single, coherent theory of everything. If, as Grok 3's findings suggest, quantum tunneling has a fundamental connection to the underlying structure of spacetime itself, it might very well represent the crucial missing link that physicists have been searching for, potentially paving the way for a unified theory that describes all the fundamental forces and particles in the universe within a single, elegant framework. However, it's crucial to maintain a degree of realistic perspective. Science is a slow and meticulous process, built upon rigorous testing and peer review. The experiments needed to definitively validate or refute Grok 3's groundbreaking hypotheses will likely take years to design, conduct, and analyze. And even when the data comes in, interpreting the results and reaching a consensus within the scientific community could spark decades of further debate and investigation. Still, the wheels of scientific progress are now turning with renewed vigor, and Grok 3 has undeniably provided us with a tantalizing and potentially revolutionary roadmap to pursue. If Grok 3 is indeed correct, and quantum tunneling is far more than just a probabilistic quirk, if it's a fundamental key that unlocks deeper aspects of reality's hidden architecture, then we might indeed be standing on the precipice of a new quantum revolution. A revolution poised to unlock the secrets of extra dimensions, the mysteries of time, and perhaps even the tantalizing possibility of interactions with other universes. Or perhaps this will turn out to be another fascinating anomaly, a subtle misinterpretation of data that ultimately leads us down a different, albeit still potentially fruitful, path of scientific inquiry. The truth, as is often the case in science, remains elusive for now. But the possibilities that Grok 3 has illuminated are undeniably dizzying. Think about it. If fundamental particles can, in some sense, rewrite the rules as they tunnel, what does that imply about the very nature of the universe and our relationship to it? Could we one day learn to harness this fundamental ability to achieve feats that currently reside firmly in the realm of science fiction? Teleportation, time travel, or even communication with hypothetical parallel worlds? Or are we perhaps chasing shadows, allowing the excitement of a novel AI-driven discovery to overhype what might ultimately be a more conventional explanation? This groundbreaking discovery challenges many of our most deeply ingrained assumptions about how the universe works, and it's now up to us, scientists, dreamers, and curious minds alike, to grapple with its implications and to diligently pursue the truth wherever it may lead. What do you think? Could Grok 3's findings truly change the game, ushering in a new era of scientific understanding and technological innovation? Or is this just another intriguing cosmic tease, a fascinating anomaly that will ultimately be explained within the existing framework of physics? If you're captivated by the kind of mind-blowing discoveries that push the boundaries of our understanding of physics, artificial intelligence, and the vast, enigmatic universe we inhabit, then don't miss out on future explorations. Subscribe to our channel now to have the latest groundbreaking insights and thought-provoking discussions delivered straight to your feed every week. And let's keep this fascinating conversation going. Drop a comment below and share your thoughts. Do you believe that quantum tunneling could one day lead to practical applications like teleportation or even time travel? What are the most mind-bending possibilities that Grok 3's discovery has sparked in your imagination? Let's discuss. As we continue to explore these incredible frontiers of science, I want to wish you all the very best of health and a mind that remains open to the wonders and mysteries of the universe. Thank you for joining me on this incredible journey of discovery.